When we look at the rate law, there are two different orders that we can consider. One is the order with respect to that reactant, and when we say order, what we mean is that exponent that is that we're raising the concentration to. Or we can talk about the order of the reaction, and so that is the overall or the sum of all of the exponents in our rate law. So for example, if we're looking at the rate law of nitrogen monoxide and oxygen, our order with respect to nitrogen monoxide is second order. With respect to oxygen, because there is no exponent written, it is first order. And if we add those together, 2 plus 1, the overall reaction order is third order. There are a couple different orders of reaction that happen fairly commonly. So the first that we're going to talk about is zero order. And this means that there is no relationship between the concentration of the reactant and the rate of the reaction. So if we have a reactant, if we double its concentration, it's going to have no effect on how fast the reaction occurs. So this includes reactions like sublimation reactions or reactions that happen on the surface of a catalyst. If a reaction is first order, the rate is directly proportional to the reactant concentration. And so if we double the concentration of the reactant, it is also going to double the rate of the reaction. And so these tend to be reactions that are first order. So things like decomposition reactions, where we're breaking one component down into multiple products. If we have a reaction that's second order, the rate is dependent on the concentration of our reactant, but it is the square. So the rate will increase. If we double the reactant, it will quadruple the rate of the reaction. And there are lots of examples of this. If we look at the relationships graphically, let's start with the concentration of our reactant and the time. So our zero order reaction has a linear relationship between our concentration and the time that it takes the reaction to occur. The first and second order are not linear. If we look at the rate of the reaction versus our concentration, if we have a zero order, we have a horizontal line. The rate does not depend on the concentration of our reactants. The first order is a linear relationship with our reactant concentration, and the second order is not a linear relationship. The order of a reaction can be determined, but it has to be done experimentally. So in the experiments that we set up, we're going to change the amounts of the starting concentrations of our reactants and see the effect that it has on the rate of the overall reaction. This will allow us to determine how the rate is impacted by the change in just one of the reactants in the experiments. And we have to compare two different experiments in order to determine the change. Let's determine the order and rate constant for this reaction. We're going to look at nitrogen dioxide plus carbon monoxide, giving us nitrogen monoxide and carbon dioxide. Now there's a couple different ways that we can go about doing this in order to find the order. One is by inspection. So we compare two different reactions where the concentration is held constant for one of the reactants. So if we look at experiment 1 and experiment 2, the carbon monoxide is held constant. Our concentration doubles for nitrogen dioxide. And when we look at our rate, it increases by a factor of 4. So this means that the order for our nitrogen dioxide is going to be second order. If we compare experiment 2 and 3, now the nitrogen dioxide is held constant and the carbon monoxide concentration is doubling. And when we look at the rate, there is no change. So there's no change even when we double the concentration. And that means that our carbon monoxide has an order of 0. Now, alternatively, we can do this mathematically, where we compare the rates mathematically. So I'll show you how to do that. We take rate of experiment 1, and we use the rate law. And we compare it, divide the whole thing by the rate law for experiment 2. We can determine our order. We'll plug some numbers in. So we're comparing rate 1. We don't know K yet, but that's okay. We can plug in a concentration of our N2O to the X, concentration of CO to the Y. Oops, our CO concentration, I'm sorry, is 0.10. Let me make that a little clearer. We divide that by the rate for the second reaction. Okay. And we simplify it. So we're going to, anything that remains constant is going to cancel out of our equation. We can simplify it, divide our rates. And now we have to figure out how we can get that x out of the exponent so that we can solve it. And we're going to use the properties of logs or natural logs. So if we take the natural log of both sides, we can bring that exponent down. And solve for it. Okay. And we find that x is 1.966 or an order of 2. We can do the same thing for our y. So we're going to plug in the numbers, look at rate 2 versus rate 3. Plug it into our rate law. Use our concentrations. Again, we don't know K yet, but that's all right. And now we're going to hold the concentration of our nitrogen dioxide constant. And we know X, so we can plug that in now. Concentration of carbon monoxide, we're trying to figure out its order. So our constant and the concentration of nitrogen dioxide is going to cancel out. We're going to get approximately 1 is equal to, and we're going to have to take the natural, or, well, before we get there, let me write this out. Now we can take the natural log of both sides in order to get the exponent out of, or to bring the exponent down. Take the natural log of 0.5. Natural log of 1 is 0, and so y is equal to 0. We end up with the same answer that we did when we looked at it to inspect it. Now we want to find the rate constant. In order to find the rate constant, we can choose any one of these experiments in order to plug the numbers in. So just out of the ease of it, I'm going to pick the first one. So the rate of experiment 1. And I'm going to simplify because the carbon monoxide is a 0 order. It is not included in our rate law. So we're just looking at the NO2. We can plug some numbers in and solve for K. So our rate is 0.0021 equals K. Our concentration is 0.1 at this point. We can divide both sides by 0.1 squared. And we get that K, our constant, is equal to 0.21 1 over molarity times seconds, or molarity to the -1, seconds to the -1. Okay, so pause the video and determine the rate law and the rate constant for ammonium and nitrite reacting. Okay, so we are going to use experiment 1 and 2 to find the order with respect to NH4. So we're going to take rate 1 and we're going to try and find X to start with. We're going to divide that by rate 2. Okay, we can plug some numbers in. So our rate 1 and is 10.8 times 10 to the -7. So that is in our table. Molarity per second. Divide by rate 2. We don't know K yet. Our ammonium concentration 0.02. The X. And 0.06 to the X. Again, our nitrite is going to cancel out. The K will cancel out. I have the natural log of the left side is equal to X times the natural log of our concentrations. And we get negative 1.0955 equals X times negative 1.0996. Divide to get X by itself. And we get that X is equal to 0.0997, which is first order. Now we can do the same thing with our Y, but for Y we're going to pick 3 and 4 because our concentration of ammonium is held constant. going to get our rate. For experiment 3 and 4. Our ammonium is held constant, but our nitrite is changing. Now, if you did this by the inspection method, that's perfectly fine as well. So we're going to take the natural log of both sides. That brings our exponent down. And we end up with y equals 1. So the order with respect to the nitrite is also 1. Now to find K, we're going to plug it into our equation and solve for K. So we'll go with the first reaction. We'll divide by our concentrations. Let me move this over just a little bit. And both of our orders are to the first power. And so our K equals 2.70 times 10 to the -4th meters to the -1 seconds to the -1. So our overall rate equation is rate equals 2.70 times 10 to the -4th. Oops. Times our ammonium to the first power and our nitrate to the first power, to the first order. So overall, our reaction is a second order reaction.